All right, we're going to go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover securing the Edge AI with wolfSSL on the STM32N6, presented by wolfSSL Senior Software Engineer David Garsky and ST Microelectronics Mina Rumenbakis. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, David and Mina will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections, and we have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DL178 support, a FIPS 140-3 certification and a FIPS Ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I would like to turn it over to David and Mina to discuss securing the Edge AI with wolfSSL on the STM32N6.
Thank you, Emma. My name is David Garsky, and I'm a senior software engineer at wolfSSL. And my co-presenter today is Mina Rumenbakis from ST. Together, we're going to talk about securing the Edge AI with wolfSSL on the STM32N6. I'll do a quick introduction of our company. Mina will talk about the N6 and some of the other STM32 products. I'll talk about wolfSSL products, and then we'll go over some of the security features of the N6 and best practices, and we'll end with a live demo showing our wolfSSL Cube Pack running on the N6. As Emma mentioned, we started in 2004. The CYAZL product, which is today our wolfCrypt wolfSSL, was written in 2006, and that's still what we have today. It's added so many features and so many customers since then, and we've grown incredibly. We have over 2,700 OEM customers, 17 resale partners, including ST, and we secure over 5 billion connections at any one point in time, just because of the types of products that we know we are in. This is our suite of products, all built around the cryptographic engine known as wolfCrypt. It's FIPS 140-3 and DL178 certified at the DAL A level. We have all these different products kind of built around those things, and I'm going to talk about all of the top ones. The ones I won't talk about in detail are the Wolf Entropy, which is a software-based TRNG. Basically uses minor cache timing differences. It is in our standard wolfCrypt library, and it's called Entropy Memus. We also have a PKCS11 provider that uses wolfCrypt and can also use wolfTPM underneath that. There's a few other secure elements it supports. And in wolfSSL, you can also use and consume PKCS11. So we can both be a provider and a consumer. One of our newest products is called wolfHSM. And despite its name, it's actually a software library that's used to take advantage of hardware platforms that have a secure core or a secure area of the chip. So for example, the N6 is a Cortex M55, and it has trust zone. We could leverage wolfHSM in the trust zone, and there are long-term plans to do that. Wolf Engine and Wolf Provider are basically just plugins for OpenSSL so that you can use our wolfCrypt library. And most customers do that to fulfill FIPS 140-3 requirements. Then we have lots of different wrappers and interfaces like JavaScript, JCE, C#, Python, command line utility. And we also have curl. The curl library is part of our portfolio. We offer support for it. And there's a tiny version of curl which can be used on embedded devices, which is pretty neat. wolfSSL is an ST authorized partner. We work really close with ST to make sure we support all of their latest hardware. We're continually adding support, and we have CubeMX packs or cube packs for wolfSSL, wolfCrypt, wolfMQTT, wolfSSH, and wolfTPM. So these packs make it really easy to just check a few boxes and actually have the library installed and usable. It also provides a nice GUI interface for selecting features. I will show you the wolfSSL cube pack later. We also have support for most of the STM32 parts in wolfBoot. The N6 is a work in progress. It is not done yet. We are an open source product. And what that means is that you can go onto our website or you can go onto GitHub and you can download any of these libraries in full form, everything. You can build, test them out. We'll provide free pre-sale support. If there's features that are missing you need or you might need help porting, we offer consulting services. All the support is direct from engineers like me. All right, so now Mina is going to talk about the STM32N6.
Thanks, David. And hello, everyone. My name is Mina Bacchus, and I'm a product marketing engineer with ST Microelectronics. And David invited me here today to talk to you a little bit about one of our newest devices, the STM32N6. This is the first STM32 device, I shouldn't say device, the first STM32 microcontroller with a hardware-dedicated neural processing unit to help accelerate your AI applications. In addition to that, you'll see some other firsts in the coming slides, but we're very excited about this new STM32 series, and hopefully it fits your application use case very well. And before we dive into the details of the STM32N6, I did want to briefly go over the full STM32 portfolio. A couple of notes: the dark blue headers on the series implies it's the latest product generation. In yellow are products or new series or lines introduced in 2024. And in purple are announcements and demos that were done at Embedded World. And then on the top right, you see the extra highlight there for the STM32N6, which we will focus on today. So on the bottom here, you can see we have all of our wireless MCUs, including the WL and WB series. Above that, we have our ultra low power series, including the newer STM32U0, U5, and the newest STM32 series is the U3. Above that, we have our mainstream MCUs, include the low-cost C0, the G0, and then the mixed signal G4. Then we have our high-performance MCUs, including our H5, H7, and the N6, which we will talk about today. And then above that, we have our Linux class processors in the MP1 and the MP2 families. And another important thing to note is that all the STM32 devices you see here are on our rolling 10-year longevity commitment. So you can expect all of these devices to be available for the foreseeable future. So to dive straight into the details, this is the full block diagram of the STM32N6 device. As I mentioned earlier, there are a few unique aspects to the N6, and that includes our first Cortex M55 core. This device does run 800 megahertz, but is the first M55 device from the STM32 family of products. It's also the first microcontroller, as I said, with the neural arc accelerator to accelerate your AI applications. We do also have a graphics version of this chip that does not include the AI accelerator if that's not something you're looking to take advantage of. Moving on through the block diagram, typical use case system devices with our unique ID, Watchdog, CRC, crystal, and oscillators, external crystal and internal oscillators. The memories here, so I've got 4.2 megs of contiguous RAM internal to the device. So that's all on chip. But one thing you'll notice, there is no on-chip flash. And that's meant to allow for flexibility in your design. So instead of the on-chip flash, we have a lot of external memory interfaces, including a HexaSPI port, OctoSPI, 2 SDIO interfaces, and then our FMC, the flexible memory controller, that gives you quite a few memory options there. One thing that's not highlighted on this block diagram that I do want to mention is we actually have a Memory Cipher Engine. And what that allows you to do is to essentially do on-the-fly encryption, decryption on any memory region that you'd like. It's done by region, and it has a pretty granular approach to how you can implement it. But this allows you to securely encrypt your memory when it is stored off chip on this device. That's unique to the new with the N6, and worth looking into if that's of interest. Moving on to the camera and graphics side of it, on this device, we do have a MIPI CSI2 with 2-lane interface. In addition, we still have our parallel 16-bit interface, and then those can also hook up to our internal image signal processor to help enable some advanced imaging on those cameras. Below that, you have our graphics and multimedia here with our Chrome Art accelerator, Chrome GRC, and NeoChrome accelerator. All of these are designed so that you can drive some advanced graphics on our microcontrollers, and that can hook up to this LTD TFT display controller. In addition to that, we have our JPEG hardware accelerator that can enable things like motion JPEG, but maybe more importantly, our first H.264 encoder on a microcontroller as well. So as you can see, between the display, the encoder, the camera, and the memory options, it allows for a very flexible implementation for your use case and application in terms of driving displays, taking camera data inputs, and then being able to use this M55 core to 800 megahertz with the ART accelerator potentially for AI applications to really drive some advanced applications. Beyond that, I'll go over here to the connectivity. We have 3 CAN ports, 2 USB interfaces, 1 USB-C power delivery interface. We do have 3 I2C in addition to 2 I3C interfaces, plenty of UARTs and SPIs, including a low power UART. And then we also have a gigabit Ethernet port with time-sensitive networking functionality. This is also our first microcontroller with that supports the gigabit Ethernet interface. On the audio side, we have SPDIF, SAI, and MDF and ADF filters. On the analog side, we have our temp sensor, 2 12-bit ADCs that can run up to 5 megasamples per second, and then lots of timers, including 2 16-bit motor control timers, some low power timers, and then more general purpose 16 and 32-bit timers. On the security side, in addition to the MCE Memory Cipher Engine that I mentioned, we also can support secure boot, a secure real-time clock, an analog true random number generator, crypto and hash accelerators. We do have tampered PIDs and one-time programmable memory that is fused, that is 8 kilobytes in size. And on this slide, we can see the full portfolio of the STM32N6 devices. As I mentioned, there is no flash on this device. That will come through the external memory interfaces that I mentioned, but all of the devices do have that 4.2 megs of on-chip RAM. And then due to the high pin count and density of the device, considering all the I/O that I mentioned on the previous slide, you can see that we do focus on the BGA packages. On the small side, we're looking at a 6x6 package that is 0.4 mil pitch. We do have 0.5 mil pitch, 0.65 mil pitch, and then 0.8 mil pitch package options as well. And then the biggest one is that 14 by 14 with 264 pins coming out. The color coding here, the light blue is without the hardware crypto engine. The dark blue is with, and then the bottom half of these devices are considered what we consider our graphics line, and because it does not include that AI accelerator, whereas the top half of these devices highlighted with the yellow block does include that AI engine for any AI use cases you may have. And I did want to spend a second here to quickly point out our eval boards. On the left, you see a Nucleo N657 board. This is designed to be easily adaptable to your pinouts with our Morpho connectors on the edge in a very low-cost device. In the middle, we have our DK board based on the N6570. And that's for advanced prototyping, including the AI. It does have the Morpho connector and Arduino connector, also MIPI, USB connectors. The Gigabyte Ethernet port that I mentioned is brought out here. And here we also include 32 megs of hexaram, the audio jack, and an SD card for some additional memory options. Then on the right here, we have our BCAMS IMX expansion board. This is a camera module, the same one actually that works with our MP2 eval board. All these are available today through our channel partners. And in addition to the eval boards and our IMX expansion camera module, we do have some ST-specific camera modules here, including the ST-VD55G1 and VD66GY sensors. These are add-on cards with the flex cable that can connect to the board. And then on the right here, we also have a camera module board, and that's for plugging in any ST BrightSense Pro module with a 22-pin connector and a flex cable to the N6 board. We do have more information on these modules available online. And then the last slide from me, I wanted to go over the full STM32 ecosystem. And that starts with the STM32 Finder and CubeMX tool. These let you go through and find the best solution, be it an actual MCU or a board itself. We also have an example selector available in the tool, but this lets you very quickly and easily figure out what's the best STM32 solution for your needs. The CubeMX tool takes that a step further and is by far my favorite tool. It includes a pin selector, so pin mux tool, a clock tree tool, power consumption calculator. It also does initial code generation as well. So the CubeMX tool is a great place to get started for STM32 enablement. Next up, we have our MCU packages. So STM32 series, including the N6, does have its own package, and that helps facilitate the code generation, but also comes with a number of example projects. Beyond that, we have our expansion packs. This helps facilitate things like additional ST hardware. Maybe you want to add an NFC device, even GPS, whatever it might be. We have expansion packs to help facilitate other products from ST. And we also have partners that help expand our ecosystem here. And wolfSSL is a big player there. They have their own expansion packs available within the STM32 Cube MX tool. Then up is the Cube IDE. This is an Eclipse-based IDE, free of charge, so it helps you do all your development in the STM32 family of devices. Next up is the Cube Programmer. This programs both on-chip and off-chip flash on STM32 devices. It also kind of tools around with the option bytes, so changing the option bytes in the device can be done through the Cube Programmer as well. And then last up here is the Cube Monitor. This is mostly for development and debug. It lets you do real-time analysis of your device while it's running. Really great way to get feedback in the real-world environment. And then I actually had to go through and add these to the slide because our ecosystem is so extensive, but we also have our AI expansion pack. This is to help facilitate and do development using any AI applications you have. Again, this is to help you get your feet underneath you quickly and get up and running quickly with our AI suite of tools. And then the AI accelerator that you see on the N6. It doesn't have to target that AI accelerator. Obviously, it's going to give you more performance, but we can run AI algorithms on all STM32 devices. And then in addition to that, the ST BrightSense and ISP IQ Tune tools. This is the camera modules, and the IQ Tune is a PC application that helps tune your camera for your use case. And then obviously we do have an extensive partner program with a number of different solutions there. The free RTOS, ThreadX, and Zephyr for RTOSs, IAR, Kyle, and Visual Studio Code for development environments. And we do have an extensive partner solution, not on the slide, but obviously I'm about to pass back to David, but wolfSSL is definitely a key partner for us. And they have a number of great solutions that run on STM32. And with that, I'm going to pass it back to David at wolfSSL to go through some of his, extensive portfolio as well. Thanks, David.
Thank you, Mina. Now I'm going to talk about our wolfSSL products. So all of our libraries, they're open source as GPL v3, and then we also have a commercial license that's available if you don't want to use GPL. All the libraries are written in C at the CD9 compliance level, which means it'll work with any C compiler. We also have some inline and pure assembly that is optional for performance reasons. All the libraries are designed for portability with stable API interfaces. We have build time support for enabling and disabling features to allow reducing code size and memory use. And as I said, we have performant options for higher-end systems for assembly speedups. So even on this platform, a Cortex M55, we have assembly optimizations for pretty much all the algorithms. I'll go through that in more detail. There are no external dependencies. It can be built and run in bare metal and supports any OS. All of our documentation is generated from an online repository, and it's on our website as PDFs generated daily. wolfSSL supports all the latest TLS and DTLS 1.3 client and server. Minimum footprint size is about 20 to 100 kilobytes. And runtime memory usage is between 1 and 36K, depending on where you're at in the handshake and which algorithms you use. We're transport agnostic, so we'll have some customers using, for example, TLS over Bluetooth or a UART, but typically it's a socket, and we have lots of built-in support for different TCP stacks. You can also just register your own send receive callbacks if you want to use your own transport. We support all the revocation with CRL and OCSP. We have Linux kernel module support. We have an extensive OpenSSL compatibility layer with over 1,900 APIs. We support certificate generation, so creating a certificate signing request or even self-signing certificates. We have a certificate manager component that allows you to load trusted certificates and verify chains. That's what's done through TLS, but you could also use it separately. And then we have all of the post-quantum support, including hybrid post-quantum and Chimera certs. So that's the dual algorithm certificates. All of our abstraction for the OS level, time, mutex, threading, it's all abstracted, which makes it very easy to port. We have support for many different cryptographic hardware modules, including external key stores like PKCS11, TPM 2.0, HSM, including wolfHSM, and secure elements. wolfCrypt has support for all of the latest asymmetric and symmetric algorithms. This is just a small list of them. And then we have post-quantum support for ML-Chem, which was Kyber, and MLDSA dilithium. We're working on adding post-quantum algorithms into our FIPS certificate right now. We have our own implementations of all of these that we've done, and most of these I think we're working on the Kyber assembly speedups right now, but the rest of these are already there. So wolfCrypt has been certified at the FIPS 140-3 level 1. That's certificate 4718. I believe there's another certificate that just got announced a couple weeks ago. We have worked with customers at level 2 and 3. The DO-178 is a safety critical certification, DAL-A being the most critical, and most of wolfCrypt has been through that, including wolfBoot and wolfTPM. CNSA 2.0 compliance, so NIST in NSA defines the timelines for integrating post-quantum support, depending on the types of products you have. Of course, we have all of those, and we support all the higher levels of Kyber and dilithium that are required, including ASGCM 256-bit. For European customers, there's an EU mandate that's coming around. It's called the Cyber Resilience Act, CRA. And basically, any connected products need to comply by 2027. Security needs to be designed early and a core part of the product. It needs to have secure boot and a mechanism for secure update. There has to be a published bill of materials for the software, and you must provide security support for a minimum of 5 years. CRA does have fines for noncompliance, and you can read about this. So wolfBoot is our secure bootloader. It is written in C for bare metal use. It conforms to an RFC 9019, which is a firmware update architecture for IoT. It's a good read. It's small footprint, so it's designed for small embedded devices. Typically, we see the bootloader in the 10 to 16 kilobyte range. It's memory safe, so there's no heap use, no malloc free. It's all deterministic. We use a really simple partitioning header scheme and support for multiple partitions. We've abstracted all of the hardware APIs, which makes it easy to port to new hardware where you might need to adjust the CPU speed or implement flash erase write routines. We also have very portable key tools for key generation and signing. We support ECDSA, RSA, and ED 25519 and ED 448, as well as the post-quantum algorithms, MLDSA, LMS, and XMSS, including hybrid schemes of any of these. So you can do a primary and secondary. You can have 2 signatures of any of these. We support encrypted updates, and we support a public key-based root of trust with multiple keys. So for example, you can put the key store into the OTP memory, or you could leverage an external TPM. In wolfBoot, the loader handles the updates between partitions, and it's power fail-safe. So what that means is in your application, when a new signed firmware comes down and is placed into the update partition, the bootloader is responsible for installing that and handling swapping of partitions if necessary. It also is responsible for handling a rollback if there was a failure in an update. We do support self-updating the bootloader. That is not power fail-safe. We have support for external flash memories, hardware-assisted dual bank flash swapping if the hardware has it, delta updates, which is just differences between two versions. We have side channel, differential power analysis, and glitch attack mitigations built into wolfBoot. So our armor mode has, on critical jumps, it has some retries that are done to mitigate those possible power rail glitching. We have support for hardware-based SHA and PKA, the ST Safe, and the ST32N6 TPM. We have ARM Thumb2 assembly optimizations for all the algorithms that I mentioned, and we also have support for the ARMv8 trust zone, so ARMv8M trust zone. In wolfBoot, we have an example on the H5, and I believe can't remember, H5 and one other. Eventually, we'll have it for the N6 as well, but it demonstrates how to run wolfCrypt so that the APIs are done through a non-securable callable interface, as well as using our wolf PKCS11. Wolf TPM. So it's the only TPM stack designed for bare metal and designed for portable small embedded devices. It supports all of the TPM 2.0 modules, all the interfaces, all the vendors. We also implemented a stable wrapper API to simplify common use cases. So like key creation, setting up parameter encryption with an authenticated session. It's designed for low memory use, so it's only using stack, no heap. It's very modular, so features can be disabled if not needed to reduce code size. It can be built without wolfCrypt. However, there's things you can do, like importing external private keys or using parameter encryption. It has a built-in transport interface, and it's got a ton of features. But Wolf MQTT is our client library, which supports all the latest standards. So v1.3.1.1 and 5 and MQTT sensor network. It supports all the quality of service levels, 0, 1, 2. It's a very small code size, and it supports multi-threaded, non-blocking. We have lots of built-in examples, but if you have an embedded device that's connecting to a cloud, this is the tool to use. wolfHSM is portable open source abstraction for hardware. It has additional APIs that expose how to access the non-volatile storage for keys and certificates, and it can provide that isolated communication from a non-secure core to a secure core, like Trust Zone, for example. We also have PKCS11 and TPM interfaces available. We see the wolfHSM product being used very commonly in automotive applications. wolfSentry is our embedded firewall product, intrusion detection prevention. It integrates with IP stacks like LWIP, and it provides dynamic or build-time definable rules, and it can dynamically block connections based on any rules that are thresholds that are set. So here's a list of supported STM32 hardware. All of these are supported in wolfSSL and wolfCrypt, and all the if the chip has support for hashing or crypto AES or PKA, we support it on all of these. The only ones that we're still working on wolfBoot support are the MP1, MP2, and N6. All right, so now let's talk about the STM32N6 security features and some of the industry best practices. So this part is a Cortex M55, and it has a very advanced ROM. The ROM is more capable than any other STM32 parts that have been made. This microcontroller has over 4 megabytes of RAM, but it has no internal flash. So it requires an external flash memory. There's pros and cons to that, but the nice thing is you can have larger sizes. The ROM is capable of loading any, the first stage bootloader, any boot code from external flash devices. And ST has tools now for signing that firmware. So it's a hardware-based root of trust using one-time programmable memory. And using onboard hardware cryptography, it's doing integrity checks, signature verification, and it also supports an on-the-fly decryption, which is pretty cool. So they have some guides out there that describe how to do this. I'm not going to go into a lot of detail, but I will point you to those. That signing tool allows you to, sign the firmware with a header that the ROM expects, which is really neat. Our plan is to have wolfBoot fulfilling all of those same things and then making it easier to boot other things after that, leveraging those same keys. The upper region of the OTP is hidden when the BSEC engine is in a state that's called open, but it's the state that is locked down, I guess. The terminology seems backward, but that's okay. But that OTP area is used for symmetric keys or private asymmetric keys. So it's really important to use secure boot, use a hardware-based root of trust. Typically, that hardware-based root of trust is a hash of a public key. The firmware image itself is computed with a hash, like a SHA-2 or a SHA-34 hash. And then there's a signature check that happens. In this case, the hardware supports ECC, so it's doing ECDSA verification. Recommend using TLS 1.3 for any secure communication to the external world. If you're using, let's say it's a TLS session where you're a server, you have to present a certificate, and that private key should be anchored into the hardware. So you can do it a couple ways. One way that I would recommend is leveraging the onboard hardware unique key. So this is a random key provisioned at manufacturing that allows you to wrap other private keys and store them safely. That private key can be used by the hardware SAES engine. It's not exportable key, so you have to use that engine to be able to encrypt and decrypt it. wolfCrypt already supports all of that. Also consider using post-quantum hybrid or full post-quantum and the dual certs. That's a good solution. Make sure you use on-the-fly decryption encryption for the external flash memories. And this is the user manual 3453, has really good details on security guidance. Okay, so now let's give a demo of the wolfSSL Cube Pack on the STM32N6 Nucleo board. I'm going to show how to configure, build, and test it. So this is a brand new instance of a STM32 Cube workspace. We're going to do just starting a new project. We're going to go to the board selector and we're going to choose STM32N6. We're going to choose the Nucleo board. We're going to give it a name, STM32N6 Wolf Demo. We're just doing secure FSBL only. And this is using the Cube Pack 1.2.0. So because it's an ARM v8 with the trust zone, there's basically the FSBL, which is the secure side of the first stage bootloader, and then the application side. At this point right now with this demo, we're just doing a bare metal in the FSBL, and we're going to have access to all the peripherals and anything we need to run wolfCrypt. There is Ethernet on this board. I have not tried playing with it yet, but it would be very easy to set that up with wolfSSL. The demo I'm going to demonstrate or generate here actually does TLS, can do TLS. If I enable the FreeRTOS as well, and the demo fires up some tasks that will do TLS between two sessions. So while this is generating, I also wanted to show a couple things. So when I was doing the demo, I did find a couple of bugs in the STM32 hashing peripherals. So there is a pull request 9256 that will get merged in, and it'll be in a future release. Okay, so let's. So when you create a new project for the Nucleo, it'll ask for some of these peripherals. I'm not going to enable any of these, so I'm going to unselect them for now because I'm not using them in this demo. The other thing is that I did collect some benchmarks for the N6. I did find that the onboard crypto hardware was the fastest. Another thing is that it, by default, the max speed it can do is 600 megahertz. It is capable of 800, but you have to do overdrive mode. There is a tutorial I have not tried that it shows you how to do some blowing of fuses and how to drive the GPIOs to basically increase the core clock or the core voltage. One thing that I did encounter is that there are boot jumpers, and in development mode, to be able to use this board, you do need to set the boot one. You need to jumper it to be in development mode. There is, ability to change between flash boot and serial boot. And it supports all these different flash boot modes. So this part has 4 megabytes of internal SRAM, and some of that is available for different purposes in the memory map. By default, it'll use SRAM2, which is about a megabyte region. There's also an external OctoSpy flash part that's, I think it's 64 megabytes or something that you can use. And the boot ROM is responsible for loading from there and booting. It does execute in place in the peripheral. So go back to the Cube project now. Hopefully I can get it to actually open. Okay. Okay, so to start with, I want to enable the RTC external oscillator. So the low speed oscillator, I'm going to change to ceramic. So the Nucleo board has an external clock. Then we're going to go to timers and RTC, and we're going to enable the clock for the FSBL. Then we're going to go over to clock configuration, and we're going to switch it to the external oscillator. Next, we're going to turn on connectivity for the USART1. So if we can get down to it, USART1 and FSBL asynchronous. Now the virtual COM port for this Nucleo board is PE5 and 6. So I'm going to go to PE5. And I'm going to switch this to USART1TX. And PE6 is right here. And I'm going to change that to USART1RX. So you can see those two right there. Great. Next, we're going to go turn on the security peripherals. So we're going to turn on the security engine, the crypto, the hash, the PKA, RNG, and SAES. So even though I've checked those, they're not actually activated. I have to actually click activate it. Otherwise, the code will not get generated. It's just an oddity of the tool, but that is okay. After this, we're going to go turn on the wolfSSL Cube pack. Okay, so all those look good. So next we will go to the Cube pack for the wolfSSL wolfcrypt library. Make sure that this show components for context is selected to the FSBL. Otherwise, it will check the wrong box and you won't get the code generated in the project you want. So we're going to enable the test code and also the core for crypto and TLS. Now we'll open this back up and go back in here, and we have to do that same thing to activate it. All the settings here are perfectly fine by default. There is some things that are interesting. For example, the math configuration, we have several options for, for math, multi-precision, single precision, C versions of it, or assembly. So this option right here is the fastest on this board. Although right now, by default, it will use the PKA for ECC. For RSA and Diffie-Hellman, it will use our single precision ASM. It will also use the hash and AES for the STM32. All these other options are fine. There is a thumb ASM support option you can turn on if you didn't want to leverage the crypto hardware, but defaults on this are good to go. The only other thing I want to do is increase the stack space for the FSBL task. Let's see. I don't know why it's not letting me click in here. Oh, clock configuration. I probably have to resolve these. So because we turned on the USART, it's gonna resolve clocks. Okay. Now maybe it'll let me do it. Well, let's do this. Let's go ahead and save this and let it generate code. And let it switch to a different perspective. So code that gets generated is very close to complete. There's only a couple of things that we have to do to get it working. So the first is it doesn't call our example. So basically we need to call wolfcrypt demo. It's a function that already exists and being built into the code. The other thing has to do with the printf support. So by default, printf will not map to that. So inside here, I'm going to add in a little bit of code to do this. And if you're curious, inside the README for the STM32, these steps are described pretty well. So you know how to do the configuration for the pack. There's also a set of code here for how to turn on the printf support, and this set of code has helped me across all of the different demos I've done. So I'm just going to drop this up here. Everything should build now. The only thing I didn't manage to tweak was that. Let me see if it'll let me do it now. It just really doesn't want me to touch these settings. I don't have an explanation for that. So what I can do is go in here and manually adjust them. So we'll do 32K of stack and maybe 8K of heap. The other thing is that this region of memory for that SRAM2 technically goes from here up to here. And this will let me build and play with a larger subset of code here. Just extending this 1 megabyte region a little bit for the, it's called the AXI SRAM2. And the FSBL has full access to this 1 megabyte region. There's also a region before this. You can look at the memory map. The only other settings that we need to change are for the printf support for float on the benchmark. And it's just because our benchmarking tool uses float. So we go into the MPU settings and we say printf with float, and we'll do that for release as well. So at this point, things should build. Let's give it a try. See if I can close some of these things. We should see a warning because this is, I'm not including the wolfSSL example header. I could, but it's not required. I'm going to go ahead and switch to release so that we can run the benchmarks in the wolfcrypt tests. We should see numbers similar to what I posted. We'll see if this actually works. So we're going to do the release version of the build. And again, I have my boot 0 set to yeah, so 1 and 2 is set on boot 0, and on boot 1, it's 2 and 3. It allows the debugger to write this into RAM and then just jump to it and execute. Okay, going to switch to the debug perspective. It should be in main there somewhere, and execute. So we get a list of choices. So we can run a wolfcrypt test with a T, or the B would be the benchmark. So we run these. And it's taking a little long, so let's, I don't know, it was the RSA test that took a little long there. And after this, we'll run the benchmark. So just for reference, we'll go back to, I know what it is. There is, so even though we turned on made sure that the cache, actually I might not have mentioned it, but inside there's a cache on this chip. There's an instruction and a data cache. And it makes a significant difference in performance. And there are 2 lines of code that we will add to the main. So somewhere right about here is good. We will enable the iCache and the Vcache. So this makes like a massive difference. So like, for example, for running the benchmarks, we'll see this go, maybe 5 times faster. So we'll drop this. We will build again. And debug again. And this is the release build that we just did. Yeah. And run. We'll get a new menu here and run the test. Yeah, it's several times faster with the cache turned on. We'll run the benchmarks. So this is the defaults are using all the STM32 RNG, the SHA hardware acceleration, AES, and the PKA for ECC. And as you can see, the performance is really great at 600 megahertz. All the code for TLS is enabled. The only thing is that the code is not, the example doesn't work unless I have like an RTOS, like free RTOS or SimSys RTOS or something set up. But again, you can see all of those benchmarks posted. They should be pretty similar to what I collected earlier. And they look a little slower. Oh, that's GCM. Yep, they should be the same. Look a little different. We're pretty close. Oh, that's because of the 4-bit table. Yep. There was something I missed on the GCM. So GCM is an authenticated cipher, and there's a G hash that's computed, and you don't have to do this from the GUI, actually. I could show you how to do it from not the GUI. There is an option there for GCM small versus GCM 4-bit table. The 4-bit table is just a faster way to calculate that G hash in software, which is probably what's happening there. The crypto hardware has certain alignment requirements for what can be passed in and not, and also with the authentication tag for GCM. So that would be the only setting I would change. And that pretty much wraps up the demo. I would love to get an opportunity for you guys to ask some questions. Between Mina and I, we should be able to answer any more in-depth questions about this part. I don't have a lot of experience with the AI models on this part. There are other webinars that cover that, and other partners with ST that do that very well. It does have the AI engine, which is a unique feature, and the graphics. This is a highly capable microcontroller. So thank you for your time. Let's open it up for questions.
Wonderful. Thank you, David and Mina. To kick off the questions, how is the performance of the AI accelerator?
Yeah, thanks. I can take that one. I think it was on the slide, but I don't think I mentioned it when I covered it. The AI accelerator on the N6 is 0.6 TOPS or 600 GOPS, which is 0.6 trillion operations or 600 giga operations on the device. This is very capable for a microcontroller, and for reference, our STM32 which was our first device with an AI accelerator, does 1.3 or 1.35 TOPS performance. But again, for these small, low power microcontrollers, it's a very good AI engine that sits on the edge.
Wonderful. What type of power consumption can we expect with the STM32N6?
Yeah, that's another good one. I'm going to ballpark these because I don't have the numbers memorized. I believe if we run CoreMark at 600 megahertz on the device, it consumes approximately 70 milliwatts. That's with all the peripherals off and things like that. In various sleep states, because there are a number of different options, it can range anywhere from the 10 to 50 milliwatt range. And then then there's multiple standby and lower power states, and then the lowest one is something like 70, 71 microwatts in like a VBAT mode. If you're kind of trying to stress the device and use it, so we did a benchmark where we're using the AI engine the video encoder, running the graphics, and running an RTOS, and that consumed about 500 milliwatts on the device.
Wonderful. What size display can you drive?
Yeah, that's a good one because there's a part gets a lot of attention for the AI engine, but we also have the version without the AI engine. They can both run graphics. I'm going to focus on the on-chip SRAM because, again, it does have that 4.2 megs of continuous RAM on the device. So utilizing your frame buffers in there, you can do, if you have a lot of moving pieces, like actual motion or graphics playing, with double buffering, we can do 1024 by 600 with 24 bit depth. If it's less motion, just buttons and things like that, a lot of static images, you can do a single frame buffer and it'll still look really good. And with that, we can do up to 1280 by 720 with a 16-bit depth on the bits per pixel. Oh, and I
Wonderful.
should highlight,
Can we run?
sorry, I'm interrupting. I should highlight, you can
No,
add
you're all
external
good.
memory. You can add external memory and increase that. I personally don't know the full. If you wanted to really stress it and drive as big of a display as you can, I'm not sure. But using the on-chip memory buffers, those are the resolutions we can get. Thanks.
Wonderful. Can we run model created with TensorLite?
So the
David,
cube, the
Lena?
AI cube tools. Sorry, can you hear me? I'm not on mute.
Yeah, we can hear you,
Nope,
Nina. Go ahead.
you're good. I can hear you now.
Okay, thank you. So the Cube AI tools, they're extensive, and I'm not the AI specialist. We do support like TensorFlow Lite, gosh, I forget the name of it now. A number of different AI tools on the devices, though. We have a landing page both on st.com and then more details on the wiki site to talk about the AI. And we do have AI experts that can really talk in depth about this. I am not the AI expert, so maybe not the right person to answer this question. But if you have any questions, don't hesitate to reach out to your local ST contact, and hopefully we can get you the right answers.
Wonderful. Can Secure Boot be tailored for custom PKI?
That's a good question. So as far as I can tell, the boot ROM and the mechanism it has to do signature verification is tied to the PKA, which is only ECC. However, you could have, let's say, wolfBoot after that leverages different, algorithms. You could do any type of algorithm you want that supported the keys, and the key infrastructure for that is totally customizable. That's something you could do yourself. It's not like you have to rely on ST for any sort of provisioning of keys or signing. I think custom PKI is referring to the algorithm choices. Like I said, the hardware has a specific algorithm that it requires as part of the boot ROM and the security profile with the PKA. But after that, you can leverage anything you want, with wolfBoot, for example.
Great. Also, Mina, the question I just asked you, there was a typo. It was TensorFlow Lite that they were referring to. I'm not sure if that changes your answer at all, but
Yeah, I'm pretty sure we do
thought I would
support it.
mention it.
But again, I do recommend we look through the website because I just don't have it memorized. But yeah, we have extensive AI tools to help you implement these things. And I do believe TensorFlow Lite is included, but don't quote me on that. The website and our wiki site have a lot more details and information on that.
Wonderful. Does the STM32N6 have a hardware root of trust?
It does. Yeah, I mentioned it a few times. It's the OTP has a region specifically for a hash of public key that can be placed there for the boot ROM, and then that could also be leveraged going forward in wolfBoot or a second stage loader. And that is important. So that gives you assurance from, boot ROM to the first code that's being executed, that there's this trust being handed off, and then you can continue that all the way to booting the application.
Wonderful. How many active TLS client sessions can I create with wolfSSL?
So the limitation is simply memory. The most memory that's taken is during the handshake period where you're trying to establish a set of shared keys. The peak during that handshake kind of varies depending on algorithms. It can be anywhere from, 5 to 10 kilobytes to potentially 30 or more. So in theory, you could, with this device, I could see running hundreds of connections easily, without an issue.
What is the timeline for supporting wolfBoot with the STM32N6?
Well, it's as soon as possible. It really helps to have customers driving that need. Without a customer driving it, it's really as soon as when our engineers have time to do it. But I would expect it to be done before the end of the year.
Wonderful. I believe this is the last question. What is SFI?
I'll try to answer that. Maybe Mina can help me with it. But it's something that ST does for secure provisioning. It's called secure firmware install, and there's specifically areas in the OTP that allow for provisioning of keys during manufacturing, and that may include certificates. But Mina, do you have any other information to add on that?
Yeah, so you summarized it pretty well, David. It's to help the manufacturing process. So the OEM, the developer can, once the firmware is completed, they can encode it, and then we have an SFI process. So even if you love your CM or whoever's programming your devices, you can assume there might be a nefarious character or something going on, and you need to deliver an encrypted firmware. The SFI process allows your firmware to never be in the clear, essentially. Program the devices, also count the number of devices so people can't over or under produce, and just reassure you with the manufacturing process and flow that your device is secure for the full device cycle of the product.
Wonderful. Another question did sneak in. Is there a timeline to fully support CMake and wolfBoot?
Yeah, so the CMake support in wolfBoot it's not our primary. We usually just use make files. CMake was contributed by a third party. We do find more customers using it, and I do expect it to be improved over time. There isn't an immediate timeline for it, though. Sorry.
Wonderful. Well, thank you, David and Mina, for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at fax@wolfSSL.com. Thank you again, and we look forward to seeing you on October 8th for our webinar on WolfGuard FIPS 140-3 enabled wired